Hello. Today I want to talk to you about something that everyone thinks about but rarely examines carefully: the past and the future. We all have this strong sense that the past is different from the future. We remember yesterday, but not tomorrow. We can change the future, but not the past. Time seems to flow in one direction. But why? What makes the past and future different? And what can physics tell us about this? These are deep questions, and I want to explore them with you. We'll talk about memory and causation, about the arrow of time, about entropy, and the second law of thermodynamics, about the beginning and possible end of the universe, and about what physics might look like in the future. It's quite a journey, so let's begin. First, let's think about what we mean when we say something is in the past or in the future. The past is what has already happened. We have records of it, memories of it. The future is what hasn't happened yet. We can anticipate it, plan for it, worry about it, but we don't know it with certainty. And the present is this peculiar moment, right now, that seems to separate the two. But here's something interesting. If you look at the fundamental laws of physics, at Newton's laws of motion, or Maxwell's equations of electromagnetism, or even the Schrödinger equation of quantum mechanics, they don't distinguish between past and future. The equations work just as well if you run time backward. If you took a movie of planets orbiting the sun and played it in reverse, it would still obey Newton's laws perfectly. The mathematics doesn't care which way time goes, yet we certainly care. Our experience of the world has a definite arrow of time. So where does this arrow come from? Why is the future different from the past if the fundamental laws are symmetric? The answer has to do with something called entropy and the second law of thermodynamics. Entropy is a measure of disorder, of how mixed up or random a system is. And the second law says that in any closed system, entropy tends to increase over time. Things get more disordered, more mixed up, more random as time goes on. Think about a drop of ink in water. When you first drop it in, the ink is concentrated in one small region. That's a low entropy state, very ordered. But the ink spreads out, diffusing through the water until eventually it's uniformly mixed. That's a high entropy state, more disordered. And you never see the reverse happen. You never see ink spontaneously collecting itself back into a single drop. The entropy increases, and this gives us a direction to time. Or think about a cup of hot coffee cooling down. The heat energy spreads out from the concentrated hot coffee into the cooler surrounding air. Entropy increases. You never see heat spontaneously flowing the other way, making the coffee hotter and the room cooler. That would decrease entropy. This tendency for entropy to increase is what defines the arrow of time. The future is the direction in which entropy is higher. The past is the direction in which entropy was lower. Everything about the direction of time, about cause and effect, about memory and anticipation, comes back to this fundamental fact about entropy. But this raises a puzzle. If the fundamental laws of physics are reversible, where does the irreversible increase in entropy come from? The answer is that it's statistical. Let me explain what I mean. Imagine you have a box divided in half with all the air molecules on one side. That's a very ordered, low entropy state. Now remove the divider. The molecules will spread out to fill the whole box. Why? Because there are vastly more ways for the molecules to be spread throughout the box than there are ways for them all to be on one side. It's not impossible for all the molecules to randomly end up on one side again, but it's incredibly improbable. The number of possible arrangements where they're spread out is enormously larger. So the increase in entropy isn't a fundamental law in the same sense that conservation of energy is. It's a statistical tendency. Systems evolve from less probable states to more probable states. And since there are so many more high entropy states than low entropy states, systems almost always evolve toward higher entropy. The key word is almost always. In principle, entropy could decrease. The coffee could spontaneously get hotter. The ink could spontaneously collect into a drop. But the probability is so incredibly tiny that you'd never see it happen in the entire lifetime of the universe. The second law of thermodynamics is not absolutely ironclad, but it's so overwhelmingly probable that we can treat it as a law. Now here's the really important point. We live in a universe that for some reason started in a very low entropy state. The early universe, right after the Big Bang, was incredibly smooth and uniform. It had very low entropy. And ever since then, entropy has been increasing. Structures have formed, stars and galaxies, and these structures have increased the overall entropy of the universe even though they're locally ordered. This initial low entropy state is why we have an arrow of time at all. If the universe had started in a high entropy state, maximally disordered, nothing interesting would happen. There would be no direction to time, no cause and effect, no memory, no life. The fact that the universe started with low entropy and is evolving toward higher entropy is what gives us the past and future. But why did the universe start with low entropy? That's one of the deepest unsolved questions in physics. We don't know. We can describe what happened after the Big Bang, but we don't know why the initial conditions were what they were. Some physicists speculate that it has to do with quantum mechanics and the nature of time at the very beginning, but we don't have a complete theory yet. Let me talk about memory, because memory is intimately connected to the arrow of time. You remember the past, but not the future. Why? Because memory is a physical process. When you remember something, there's a physical record in your brain, patterns of neural connections that encode information about past events. Creating this record increases entropy. The process of forming a memory is irreversible. It takes energy. It generates heat. It increases the total disorder of the universe, even while creating local order in your brain. This is why memory only works in one direction. You can't have memory of the future because you can't create a record of something that hasn't happened yet in a way that decreases entropy. This might sound obvious, but it's actually quite profound. Your sense of time, your feeling that there's a past that you remember and a future that you don't, is a direct consequence of the second law of thermodynamics. If entropy didn't increase, if the universe were in equilibrium, you couldn't form memories. You couldn't have consciousness. The arrow of time and the existence of thinking beings like us are connected. The same is true for cause and effect. We say that the past causes the future, not the other way around. If I push a ball, it rolls. The push causes the rolling. But why can't the rolling cause the push? Why doesn't causation work backward? Again, it comes down to entropy. A cause is a low entropy state that evolves into a higher entropy state. When I push the ball, I'm creating a special ordered configuration. The ball is moving in a particular direction. This then evolves into a more disordered state as the ball bounces around, loses energy to friction, and eventually stops. The entropy increases, and that's why we perceive the push as the cause and the rolling as the effect. If you tried to reverse this, to have the effect come before the cause, you'd need to start with a high entropy state that spontaneously evolved into a lower entropy state. And while this isn't impossible, it's incredibly improbable. So we perceive causation as going from past to future, from low entropy to high entropy. Now let me talk about the past itself, the history of the universe. Where did everything come from? How did we get here? These are questions humans have asked for as long as we've been able to think. The scientific answer is the Big Bang theory. About 13.8 billion years ago, the universe began in an incredibly hot, dense state. Everything, all of space and time and energy, was compressed into a tiny region. Then it expanded, and it's been expanding ever since. In the first moments, the universe was far too hot for atoms to exist. It was just a soup of fundamental particles, quarks, and electrons, and photons, all bouncing around at incredible energies. As the universe expanded and cooled, quarks combined to form protons and neutrons. Then protons and neutrons combined to form the nuclei of hydrogen and helium. But it was still too hot for electrons to stick to these nuclei to form atoms. The universe was opaque, filled with a plasma where photons constantly scattered off free electrons. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons to bind to nuclei. Atoms formed. The universe became transparent. The photons from that era have been traveling through space ever since, and we can detect them today as the cosmic microwave background radiation. After that, gravity started to do its work. Tiny variations in density, regions that were slightly more dense than others, attracted more matter. Over millions of years, these grew into the first stars and galaxies. Stars formed, burned through their nuclear fuel, and exploded as supernovae, creating heavier elements. These elements became part of new stars and planets. Eventually, on at least one planet, and probably many others, conditions were right for life to begin. That's our past, as far as we can tell. From the Big Bang to the formation of galaxies and stars, to the creation of our solar system about 4.6 billion years ago, to the emergence of life on Earth, to the evolution of complex organisms, to the development of human civilization. It's an incredible story, and we've figured out much of it by careful observation and clever reasoning. But there are still mysteries. What happened in the very first instant of the Big Bang? What was there before the Big Bang, if before even makes sense? What caused the Big Bang? Why does the universe have the properties it does, the particular forces and particles? These are questions we're still working on. One idea is inflation, a brief period right at the beginning when the universe expanded exponentially fast, much faster than the speed of light. This would explain why the universe is so uniform, why it looks the same in every direction. But we don't know what caused inflation or what it really was. It's still a hypothesis. Another mystery is dark matter and dark energy. We've discovered that most of the universe is made of stuff we can't see directly. Dark matter doesn't emit or absorb light, but we can detect it through its gravitational effects. Dark energy is even stranger. It's causing the expansion of the universe to accelerate. We don't know what either of these things really are. They're placeholders, names for our ignorance. Now let me talk about the future. What's going to happen? Where is the universe going? Can we predict the future? In principle, If you knew the exact state of every particle in the universe and you had the equations of physics, you could calculate what would happen next. You could predict the future. This is called determinism. The laws of physics are deterministic. Given the initial conditions, the future is determined. But in practice, we can never know the exact state of everything. There are too many particles, and quantum mechanics adds an additional layer of uncertainty. The Heisenberg uncertainty principle says you can't know both the position and momentum of a particle with perfect precision. So even in principle, there's a limit to how well we can predict the future. And then there's chaos. Even deterministic systems can be chaotic, meaning that tiny changes in initial conditions lead to huge changes in the outcome. Weather is like this. That's why weather prediction is only accurate for a few days. A small error in measuring today's conditions grows exponentially, and soon your prediction is completely wrong. So while the universe might be deterministic at the fundamental level, we can't predict the future in detail. We can make statistical predictions. We can say what's probable, but we can't know for certain. For the far future of the universe, we can make some educated guesses based on what we know about cosmology. The universe is expanding, and that expansion is accelerating. If this continues, and we have no reason to think it won't, then galaxies will spread farther and farther apart. Eventually, billions of years from now, distant galaxies will be moving away from us so fast that their light will never reach us. The observable universe will shrink. In the very far future, trillions of years from now, all the stars will burn out. Star formation will stop when all the available gas has been used up. The universe will go dark. Black holes will be the last objects with significant energy, but even they will eventually evaporate through Hawking radiation. In the unimaginably distant future, perhaps 10 to the 100 years from now, even the black holes will be gone. The universe will be cold, dark, and empty. Just a thin soup of particles in an ever-expanding space. Entropy will be at its maximum. Nothing interesting will happen anymore. This is called heat death. Of course, this is just our current best guess. The universe has surprised us before. Maybe there's something we don't understand that will change this prediction. Maybe the dark energy will change. Maybe there are cycles of expansion and contraction. We don't know. But based on what we know now, the far future looks bleak for complexity and life. Entropy increases, order dissolves, and eventually everything reaches equilibrium. That's the ultimate fate dictated by the second law of thermodynamics. Now, what about the future of humanity? What about the future of science? These are questions I find more interesting and more hopeful. Humanity has come an incredible distance in a very short time. A few thousand years ago, we were hunter-gatherers. A few hundred years ago, we developed science and began to really understand how nature works. In the last century, we've split the atom, gone to the moon, decoded the human genome, built computers, and connected the world with the internet. What will we do in the next century, in the next 1,000 years? I don't know, but I can imagine some possibilities. We might develop fusion power, giving us nearly unlimited clean energy. We might send humans to Mars and beyond, becoming a multi-planet species. We might develop artificial intelligence that's smarter than us, for better or worse. We might cure diseases, extend human lifespan, maybe even find ways to upload consciousness into machines. Or we might destroy ourselves. We have nuclear weapons. We're changing the climate. We're creating technologies we don't fully understand. The future isn't guaranteed to be good. It depends on the choices we make. As for the future of science, I think there's still so much to discover. We don't have a theory of quantum gravity. We don't understand dark matter and dark energy. We don't know if there are other universes. We don't fully understand consciousness. We're still learning new things about biology, about how life works at the molecular level, about evolution, about ecology. There are big questions we haven't answered. How did life begin? Are we alone in the universe? What is the ultimate theory of everything that unifies all the forces? Can we reconcile quantum mechanics and general relativity? What really happens inside a black hole? What happened at the Big Bang? I believe we'll make progress on these questions, not necessarily in my lifetime, but over the coming decades and centuries. Each answer will lead to new questions. That's how science works. We solve one puzzle, and we find more puzzles underneath. It's puzzles all the way down, but that's what makes it exciting. If we knew everything, if there were no more questions, science would be done. But we're nowhere near that. We're still at the beginning. We're like children exploring a vast landscape, and every hill we climb reveals more territory beyond. Let me come back to something more philosophical. What does it mean to think about the future? When you imagine tomorrow, or next year, or your old age, what are you doing? You're creating a mental model, a simulation based on your knowledge of the past and your understanding of how things work. But the future doesn't exist yet. It's not real in the way the present is real. Some philosophers argue that only the present exists. The past is gone. The future isn't here yet. So all that's real is this moment, now. Others argue that the past and future are just as real as the present, that they all exist in what's called the block universe, a four-dimensional structure where past, present, and future are all laid out like space. Physics doesn't really tell us which view is correct. Einstein's relativity shows that simultaneity is relative. What I call now depends on my motion. An observer moving at a different speed would have a different now. This suggests that the division between past, present, and future is more subjective than we think. But it doesn't definitively prove the block universe. My own feeling, and this is just a feeling, not a scientific statement, is that there's something special about the present. The present is where things happen, where the universe actualizes one possibility out of many. The past is fixed, determined. The future is open, uncertain. The present is where the transition happens. But I could be wrong. Maybe the future is just as determined as the past, and our feeling of free will, our sense that we're making choices that affect the future, is an illusion. Maybe everything is already decided by the laws of physics and the initial conditions of the Big Bang. This is the old debate between determinism and free will, and I don't think physics has definitively resolved it. What I do know is that regardless of whether the future is predetermined, we don't know what it is. We have to make decisions as if our choices matter, as if the future is open. And for all practical purposes, it is. We can't predict the future perfectly, so we have to plan, to hope, to work toward the outcomes we want. Let me talk about something more practical. How can we think better about the future? How can we make better predictions? How can we prepare for what's coming? One thing is to understand probability. The future is uncertain, but it's not completely unknown. We can assign probabilities to different outcomes based on our knowledge. The sun will probably rise tomorrow. The probability is not exactly 100%, because maybe some catastrophe will destroy the Earth, but it's very, very close. Will there be a major earthquake in California in the next 30 years? The probability is high, maybe 70 or 80%, based on geological knowledge. Will humans colonize Mars in the next 50 years? I don't know. Maybe 30%. It depends on so many things: technology, economics, politics, chance events. The point is, we should think in terms of probabilities, not certainties. The future is a distribution of possibilities, and we should consider multiple scenarios. Good decision-making requires thinking probabilistically. Another thing is to learn from the past. History doesn't repeat exactly, but it rhymes. By studying what happened before, we can make better guesses about what might happen next. That's why history is important. It's a laboratory for understanding human behavior and social dynamics. We should also be humble. Most predictions about the future turn out to be wrong. People in the past imagined futures that never came to be. We imagined flying cars and moon bases, but we didn't predict the internet or smartphones. The future has a way of surprising us, so we should hold our predictions loosely. We should be prepared to update our beliefs as new information comes in. We should avoid being too confident. The future is genuinely uncertain, and pretending otherwise leads to bad decisions. Let me talk about something else: the nature of progress. Is the future necessarily better than the past? Are we progressing towards something? In some ways, yes. Technology has advanced. Science has given us a deeper understanding of nature. Medicine has improved. Life expectancy has increased. Many people live more comfortably now than in the past. We've made moral progress too. Slavery has been abolished in most of the world. Rights have expanded. Democracy has spread, though not everywhere and not perfectly. But progress isn't automatic or guaranteed. We've also developed weapons that can destroy civilization. We've damaged the environment. Inequality persists. Suffering continues. The future could be worse than the present if we make bad choices. Progress requires effort. It requires people working to make things better. It requires education, science, technology, but also wisdom, compassion, and cooperation. The arrow of time says entropy increases, but locally, in small regions for limited times, we can create order. We can build, create, improve. That's what life does. That's what intelligence does. So I'm cautiously optimistic about the future, not because I think it will automatically be good, but because I think we have the capacity to make it good if we try. We have more knowledge than ever before. We have more tools. We can communicate globally. We can collaborate on problems that affect everyone. The challenges are real: climate change, nuclear weapons, artificial intelligence, pandemics, inequality, political instability. These are serious problems, but they're not unsolvable. With effort, intelligence, and cooperation, we can address them. What gives me hope is the same thing that's always driven progress: human curiosity and creativity. Our desire to understand, to explore, to build, to improve. As long as we keep asking questions, keep experimenting, keep trying new things, we'll move forward. The future is not written. It's being created right now by the choices we make. Every decision, every action contributes to what comes next. In that sense, we're all shaping the future. Not just leaders or scientists or inventors, but everyone. The future is a collective creation, and that's both empowering and daunting. It means we have responsibility. We can't just sit back and assume things will work out. We have to actively work to create the future we want. But it also means we have agency. We're not helpless. We can make a difference. Let me end with a reflection on time itself. The past and future are, in a sense, constructs of our minds. They're how we organize our experience of change. The universe doesn't care about past and future. It just evolves according to the laws of physics. But we care. We're beings who exist in time, who remember and anticipate, who plan and regret. This makes time central to human experience. We live in time. We are temporal beings. Our lives have a beginning, a middle, and an end. This gives life meaning and urgency. If we lived forever, if there were no future we were moving toward, would anything matter? So the arrow of time, the distinction between past and future, isn't just a curiosity for physicists. It's fundamental to who we are. It shapes our psychology, our morality, our sense of meaning. We remember the past and we care about the future because we're creatures embedded in the flow of time. And physics, for all its equations and abstractions, is ultimately about understanding the universe we live in. Understanding time, understanding how the past led to the present, and how the present will lead to the future is part of understanding ourselves and our place in the cosmos. The past has brought us here, to this moment. Billions of years of cosmic evolution, millions of years of biological evolution, thousands of years of cultural evolution. We're the product of all that history. And the future, it's unwritten, it's full of possibilities, some frightening, some wonderful, most uncertain. But one thing I know, the universe is knowable. We can understand it. We've made incredible progress already, and there's so much more to learn. The future of science is bright, the future of humanity. That depends on us. So let's be curious. Let's keep asking questions. Let's keep exploring. Keep learning. Keep building. Let's create a future worth living in. Not just for ourselves, but for those who come after us. That's our responsibility and our opportunity. The past shaped us. The future is ours to shape. And that, I think, is a pretty exciting place to be. Thank you.